Hello, welcome to another module in this massive open online course. So, we are looking at the properties of convex sets, or basically operations on convex sets that preserve convexity. Alright, let us continue our discussion. Let us look at another important operation that preserves convexity, which is known as an affine function. Okay, so the next important transformation that preserves convexity, and this arises fairly frequently, is what is known as an affine. This is known as an affine function. For instance, what is an affine function? Now, if you have a vector that is, for instance, let us say x bar is a vector, let us say this is your vector. Now, an affine function is a function that is of the form ax bar plus b bar, that is A is a matrix, that is multiplied by matrix and translated by the vector b bar. So, this basically this function of this form, this is termed as a function of this form is termed as an affine function. Now, under affine function, now the interesting property or its relevance with respect to convex sets is that if S is convex, this implies that f of S, that is an affine transformation applied on S, and the resulting set f of S is convex. Okay. So, f of S implies affine transformation. Affine transformation of S, or affine transformation of all elements in S, that also results in a convex set. Okay. Typically, for instance, if you take a convex set, if you rotate it and translate it, that is which corresponds to basically an affine transformation, the resulting set is also convex. Now, interestingly, what one can also show that an affine precomposition also results in a convex set. Alright. So, what is the meaning of that? That is f inverse S, if S is convex, then f inverse of S is also convex. This implies, now what is f inverse of S? F inverse of S, that is the inverse of the set under this affine precomposition, is a set of all vectors x bar such that f of x bar belongs to S. This is known as an affine precomposition. We have f of S, which is the affine composition, f inverse of S is the affine this is the affine precomposition. For instance, an application can be demonstrated as follows. Consider the following simple example. We have already seen a norm cone. Let us go back to our illustration of the norm cone. And what we have seen in the norm cone is that we have this vector x tilde, which is of the form x bar x n plus 1. This is an n dimensional vector. You have an n dimensional vector x bar and another element n plus 1th element x n plus 1, and the norm cone is basically described by the set norm of x bar is less than or equal to x n plus 1, which basically implies that norm x bar square is less than or equal to x square of n plus 1, which basically implies that x bar transpose x bar is less than or equal to x square of n plus 1, correct. Because remember, norm x bar square is simply x bar transpose x bar. So, x bar transpose x bar less than or equal to x square n plus 1. This is an alternative representation of the norm cone. Now, let us see what its affine precomposition corresponds to. So, now let us consider x bar equals p times another vector v bar and x n plus 1 equals c bar transpose v bar. So, I can write x tilde equals this vector, which is already we have seen x bar x n plus 1. This is equal to the matrix P, stacked matrix P, C bar transpose times V bar. So, this is your matrix A, B bar is 0. So, this is an affine transformation, correct, or rather this is an affine function. Okay. Now, we want to find the set of all F inverse of set. So, this is our convex set S. Now, F inverse of S will be all S or will be all let us say V bar such that F of V bar belongs to S, implies. Now, if you look at F of V bar belongs to S implies, well, we have already seen x bar transpose x bar less than or equal to x square n plus 1. Now, substituting for x bar and x n plus 1, we have x bar is, well, p times v bar transpose into x bar, which is p times v bar is less than or equal to x square of n plus 1, that is c bar transpose v bar. Remember, x n plus 1 is c bar transpose v bar, square of that, which basically implies that v bar transpose p transpose p into v bar is less than or equal to c bar transpose v bar whole square, which basically implies v bar transpose p tilde v bar is less than or equal to c bar transpose v bar whole square. Okay. And this matrix P tilde is defined as P transpose P, and you can see this is a positive semi definite matrix. So, now what you can see is this set, alright, V bar, which satisfies this by the property of the affine precomposition, right, since x bar, correct, since we said f of v bar, that is x bar, belongs to S, that is the norm cone. So, the v bar, which is the affine precomposition, which is basically which is the set corresponding to the affine precomposition, alright, that also forms a convex set. So, this set v bar such that f v bar belongs to S, which is characterized by this relation, also forms set of all v bar satisfying this, also forms this, also forms a convex set. Okay. And in fact, this is a convex cone. This is, you can think of this as a general expression for a convex cone given by the affine precomposition. Okay. All right. So, these are very interesting properties. The first one is rather simple, and which is basically says that the intersection of two sets, if two sets are convex, or if a finite number of sets, or if any number of sets is convex, their intersection is also convex. And further, if you consider an affine function f and a convex set S, then both Fs and F inverse S are also convex. Okay. All right. Let us now move on to another interesting aspect, and let us revisit the concept of norm balls that we have seen previously. We had seen this concept of a norm ball. Okay, what is a norm ball? Now remember, the norm ball was defined as follows. I have the 2 norm. This is also known as the L2 norm, which you can write as magnitude x1 square plus magnitude x2 square plus so on magnitude xn square. This is the L2 norm, and the corresponding L2 norm ball that is given as norm of x bar, that is the L2 norm, less than or equal to, for instance, r, let us say equal to 1. Okay, so this is your L2 norm ball, and we have also seen that this L2 norm ball, for instance, in 2 dimensions, this corresponds to a, this is the L2 norm ball, which is basically equal to a circle slash sphere. In n dimensions, it is a sphere. Okay. So, this is your L2 norm ball. Okay. Now, in general, we would also, one can define, now in general, one can define what is known as an LP norm. What is this LP norm? If you take a vector x bar, the LP norm indicated by this P here is basically given as magnitude x1 to the power of P plus magnitude x2 to the power of P plus magnitude xn to the power of P whole raised to the power 1 over P. Now, you can see if you set P equal to 1, P equal to 2, it reduces to the L2 norm. Therefore, it is general. So, for P equal to 2, it reduces to magnitude x1 square plus magnitude x2 square, so on up to magnitude xn square 1 over 2, that is square root of the whole thing, which is nothing but the L2 norm. Now, this can be now used to construct other very interesting norms. For instance, the L1 norm, which is one of the most fundamental and widely applied. The L1 norm is norm of x bar 1. You can see that simply reduces to magnitude x1 plus magnitude x2, that is each to the power of p, which is 1, plus magnitude xn whole to the power of 1 over p, which is again 1. So, this is simply magnitude x1 plus magnitude xn. This is the L1 norm. And the L1 norm sphere or the L1 norm ball this is given by norm x bar of 1 less than or equal to 1. This is your L1 norm ball, and for instance, to look at this, let us consider a 2D example. Consider a 2-dimensional case. If x bar equals x1 plus x2, norm x bar less than or equal to 1, this implies magnitude x1 plus magnitude x2 less than or equal to 1. Okay. Now, how to find this norm ball? You can consider 4 cases. one is x1 comma x2 both greater than equal to 0, in which case magnitude x1 is nothing but x1, magnitude x2 is x2 less than equal to 0. So, this corresponds to the first quadrant. Second quadrant, we have x1 less than 0, x2 greater than equal to 0. This corresponds to the case magnitude x1 is minus x1. So, this will be minus x1 plus x2 less than equal to, I am sorry, it is not 0, this is 1 less than equal to 1. This is the second quadrant. Then in the third quadrant, you will have both are negative, you will have minus x1 minus x2 less than equal to 1, and in the fourth quadrant you will have x1 because x1 is greater than equal to 0 minus x2 because x2 is less than 0 less than equal to 1. So, these are the four cases, and if you plot it, you will find something very interesting. You plot the L1 norm ball, and what you will observe is if you look at the first quadrant, that corresponds to x1 plus x2 less than equal to 1, which is basically this region x1 x2 x1 comma x2 greater than equal to 0 and x1 plus x2 less than equal to 1. Okay. And similarly, this will be the corresponding region in the second quadrant, third quadrant, fourth quadrant, and therefore, if you look at this, what you will observe is that this is the region corresponding to the L1 norm ball. It is very interesting. It is very different from the L2 norm ball in the sense that you can see that it has pointed edges, something very interesting. So, you can see, and this simple observation, which means it is non-differentiable. If you see, if you observe it, this simple observation leads to in fact profound implications. So, if you look at the L2 norm ball, you can see this is smooth, it has no kinks or edges. So, the L2 norm is something that is very amenable for analysis, that is, it can be easily differentiated and so on. Whereas, if you look at the L1 norm ball, something very interesting, that is a square with the diagonals along the axis. So, it is a tilted square, and being a square, it has these sharp edges at which it is not differentiable. So, this is something that is very interesting. It is a very interesting shape. So, this is not what you think of when you think of a. So, this is basically your tilted square, okay, and it is 90 degrees. These angles are 90 degrees, it is symmetric, and the diagonals are aligned with the axis, or diagonals are on the axis, that is your x and y axis, or your x1 and x2 axis. Okay. So, this is the L1 norm ball. Now, related to this is this notion. Now, we have seen the L1 norm ball. Now, something very interesting is what is known as the L infinity norm, that is what happens when p tends to infinity. So, the L infinity norm, that is norm of x bar infinity, that is defined as limit p tending to infinity norm of x bar, which is limit p tending to infinity under root of not under root, this is magnitude x1 raised to the power of p plus magnitude x2 raised to the power of p plus magnitude xn raised to the power of p whole to the power of p, which can be basically shown to be magnitude of mod xi 1 less than equal to I less than equal to n, which is basically simply the maximum of magnitude x1, magnitude x2, so on up to magnitude of xn. So, this is the L infinity norm, something that is very interesting. So, this is the L infinity norm, and now one can correspondingly derive the norm ball corresponding to L infinity norm, the norm ball. And that is naturally given as norm of x bar infinity less than equal to 1. So, this is an interesting norm. So, norm of a vector, the infinity norm is simply the maximum of the absolute values of the components of that vector, and the L infinity norm ball is basically simply norm, the infinity norm of a vector, the region corresponding to the infinity norm of a vector x bar being less than or equal to, for instance, any radius. In this particular case, you can say the radius is equal to 1. All right. So, we will stop here and continue with this discussion in the subsequent module. Thank you very much.